Okay, so up until yesterday, what we studied was about the times when the actual time when the process starts and ends does not quite matter much. What mattered was the time that the process spends in between the start of the thing that we are looking for and the end of it. So let me just share it, guys. So previously what we looked at was, let's say if we had to look at the probability that we were in some state I at time 0 and in some state j at time t, what we would write is Pij in bracket t. So t here denoted the time that we have spent from transitioning to this particular state, right? But now when we have to talk about time inhomogeneous case, which is what we'll be doing today, we can't only just, okay. Yeah, so we cannot only just, talk about the time difference. We'll have to specify what time we are starting at, because the transition rate is not constant anymore. As we have already discussed, in the time inhomogeneous case, the transition rate would differ. So the probability that you will go from healthy to sick if you are a 20-year-old will not be any more same as the probability that you will go from healthy to sick if, let's say, you are 30-year-old. Just to give you guys an example. So again, we can sit and derive all the things that we have studied for the time homogeneous case, for the time inhomogeneous case as well. But we'll stick to some derivations, and I'm going to skip some derivations because it is more or less similar. So we did not go through the all of theory again. And you guys, and if anyone is interested, you guys can, I guess, easily follow it through. I don't know why is this screen. Oh yeah, I guess no. What's happening? Oh, okay. Yeah. So now if we have to look at the same thing, so again, what I'm just going to do now is right here the probability that at time t, I find myself in some state j, given that I was in some state I. Again, now I'm not starting at 0, I'm starting at some arbitrary time s, which is, of course, I assume less than t, right? And it can be equal to t as well. But again, we know if it is equal, then there's no way a particular process can be in two different states at the same time. So that's just going to be 0. All right, so now this will be denoted as Pij, and you will have to write the time when the process starts, which is S, and the time when the process ends, which is T, in the bracket, instead of P minus S, what you would have written if it were the time homogeneous case, right? So maybe let me just write that this is time inhomogeneous, and if it were time homogeneous, what you would have had for the same thing is Pij, and in brackets would be just the time difference, right? So T minus S. T minus S is what you would have here. So again, we keep S less than or equal to T because sometimes I might just be equal to J. So you never know. And that is why if S is equal to T, then the probability we know is of course going to be 1 always. And that is something that we use as a boundary condition to solve for the differential equations that we encounter once we look for the Kolmogorov equations. So I guess this was it about the Chapman-Kolmogorov equation. And now let's say if we are talking about the transition rates. So again, what you will do is, so you'll have the same equation. Maybe I should just write this once again. So here, if you are to figure out P of S comma T, what will this be? So again, you will draw up a number line. So this number line thing is not going to change. Not exactly a number line, but I just like to call it normally. So this is time and this is state, right? SITJ. And then you plot some particular time here in between, which in this particular case, we are going to call small u. So this is what we use as our intermediate step in between. And let's just say that we are in some state K at time u, which falls in between S and T for sure. So if I want to figure out PS comma T, which is just exactly like this. So okay, maybe I should just write IJ here as well. So you want to go from I to J in time S, from time S to time T, then this will just be written now as Pi to K S comma U times Pk to J in time u comma t, so in time t minus u in total. But again, you know that this k can encompass any of the states that is possible. So what you'll have to do is the usual thing. So you do not forget the summation here. So this will be equal to summation over all the possible values of the state space that your k can ever take. So that you take into account all the sample paths. So maybe if this is my I and if this is my j, then I can reach from this guy to that guy by any methods, right? So there can be so many different possible paths which I can encounter to reach. So here I'm at S and here I'm at G, sorry, T. So just to encounter all the possible paths that you take at time U, this is K, this is K2, K3, K4 and K5 and so on and so forth. So that you take into account all the possible paths that will give you this particular probability that you are looking to calculate. Okay, so now again, when I am looking for the transition rates, so of course I'm looking for a very, very short time interval, which again we will denote as H. So remember previously what we used to write is Pijh. So this is not going to work anymore. What we will have to probably write is S comma S plus H. So that we denote that we're starting at S and then we are ending at S plus H. So the difference is H as usual. And this will be again, this can take different values depending on whether your I is equal to J or if your I is not equal to J. And again, we will have our usual assumptions, and the proof of this is kind of similar to the one that we did for the time homogeneous case. So I'm going to skip it. But the only difference that will be there, so I'm looking at, if I'm looking at I equal to J, then I will have H of mu I in bracket S. So remember when I'm writing H, it does not matter because I know that H is the time duration. But when I'm writing mu I, it matters at what time I'm going to transition, at what time I'm going to make the jump. That is why I have to specify this S here, because S is the time when I'm planning to make the jump. And that is why you will have mu IIS plus 1 plus small o of H. So again, I don't know if you guys know, but this has to be a small o, okay? You cannot write a big O here. That means something else. And this is small o of H. And again, if you have I not equal to J, then you will have H of mu Ij as usual. And again, whenever you write this transition rate, you have to write at what time you are trying to jump and plus O of H. So this will be how you define your transition rates in the case of time inhomogeneous Markov jump processes. Yeah. Any doubts in this? So I guess now that we have already cleared this, let us directly go, and what we will do is we'll try to figure out how do we write Kolmogorov's forward differential equations and the backward differential equation for the time inhomogeneous case. But again, I guess what I'm going to do is I will only derive the backwards in the class because that is a bit different than in the time homogeneous case. So let us go back to the time inhomogeneous, I would say. And what we wrote just now was this, right? This we just wrote for the time inhomogeneous case. So we had a S here and we had a S here to denote where we are starting from, and S comma S plus H here. But now let us say, okay, yeah, and this relationship will still hold true. It doesn't matter if you're looking at time homogeneous or time inhomogeneous case. This relationship that the sum of the rows of your generator matrix will add up to 0 always remains true. And yeah, so this was it about the Kolmogorov's forward differential equation. So again, remember now if you will write this Pij t plus h, what you will have is S comma t plus h. So here you will have to specify at what time you're starting. So this would be, let's say S, then this would be again, okay, so remember there is some subtle difference in the way we are defining t in this time homogeneous case and the way we define t in time inhomogeneous case. So here what t represented was the duration that we spent, right? But now in the time inhomogeneous case, t is a particular time. So if we go back, I guess maybe I should just draw it here for a good comparison. So in the time inhomogeneous case that we are trying to study now, what we have is time s here and some time t here. So it isn't that this is the t. The t would be, let's say if this is 0, then this would be your t. But again, that is of no concern to us anymore. What we care about is what happens in t minus s. So you will have some t plus h here. And to figure out the Kolmogorov's forward differential equation, remember whenever we're looking at forward differential equation, we care about the last jump, right? We make a jump at the last. And that is why if you have st here, this is the probability that you will have, and here you will do the transition. So from t to t plus h, which involves a very, very short interval of time. So let me just erase that. And I'm going to skip this whole derivation because it is exactly the same. And I'm going to directly write this equation. So now instead of just t here, you will have s comma t to denote where you start from and where you end up at. And here again, you will have something s comma t, and here mu kj. So who can tell me what time will you have here? At what time are we making this jump from mu kj? So what does this denote? At what time are we making this jump? Anyone? Let me maybe just draw the timeline again. Yeah, is this where I wrote? Yes. Yeah. So let us say if I'm trying to write the forward equation. So again, the timeline I have is S here, T here, and T plus H here. So remember, T here denotes a particular time. Not duration as in the time homogeneous case. So this is important. And now you'll make some jump from T to T plus H. So again, I'm not going to derive this, everything here. So at the end, the result that you will get is similar. So you have Pij S comma T, which is equal to, again, you take into account all the possible sample paths, and Pik S comma T. So here you have I, here you have K, and here you have J. So these are the states. And again, now if I'm making a transition from K to J, I'll have mu K J. And what should be my time here in the bracket? Can someone tell me? What do you think should be the time in the bracket with the transition rate? So maybe you could go back and refer to this. What? Where did it go? Okay.
Will it be H?
Will it be H? And why do you think it will be H, Isha?
The gap between the two.
Okay. Okay, the gap between the two. Okay. But why do you think the gap between the two matters here? Why did we write S here? We wrote S, right? We didn't write H here. So we started off at S, and then we are trying to see what happens if we make a transition from H. So always remember, whenever we are looking at the time inhomogeneous case, for the transition rates, because see again, we could have written here mu kj t comma t plus h, right? Denoting the starting time when we are trying to make the transition and the ending time. But why do we have to write this additional information when we already know that whenever I'm writing a transition rate, it is always for h interval of time, right? So what matters is only the time when I'm starting. So what you put in the bracket over there is only the time where you start or only the time where you make the jump. So here you are traveling from state I to state K from time S to time T, which is PIKS, T. And then you make a transition from state K to state J at time T. And that is denoted by mu Kj T here. Any doubts in this?
No, ma'am.
Yeah. So basically this is what you will have. And if we were supposed to write this in terms of metrics, you will get the similar thing. But again, can someone tell me how will we write this particular thing in terms of metrics now? So again, whenever we write our metrics notations, we'll again have to consider in the time, right? We cannot ignore the time. So in the time homogeneous case, we cared about the duration, but now we care about the actual times. So in matrix notations, what do you think I should write here? Anyone?
P in bracket S comma T and A in bracket T.
Yeah, right. So again, remember what we have here is partial differentiation of the probability with respect to T. And this is equal to what? So again, we cannot forget this P as well. So here I'll have PS comma T times this. So here I'll have the generator matrix. And again, what matters is just the time when I make the transition, right? So this is how you will have your Kolmogov's forward differential equation for the time inhomogeneous case. Not much difference. So again, I guess this is much easier to remember because in time inhomogeneous case, as we will see now, the backward differential equation is a bit different than what we have in the time homogeneous case. So I guess this is good. And anyways, the answer that you will get by solving this or the one that we'll see is anyways going to be the same. So until and unless I guess the question specifies to use backward, or if you are comfortable with that backward, I guess you should go for this forward differential equation. Okay, but now again, before we go for the forward differential equation, I think what we should also have a look at what happens if I want to stay in the same state forever. So let us say if I want to figure out the occupancy probability. So we'll go back to the usual example that we took. Let me just write healthy, sick, and dead. So again, now whenever I if you remember yesterday when we did the Emily, but the diagram was still something like this. So let us just try to write first forward differential
I
equation.
don't know if it's just me, but your voice is cracking.
Here and sorry is my
Yes, ma'am, it was, Professor.
Yes, ma'am.